Welcome to the lecture on phase transformations. So, phase transformation is an important phenomena, and we must know the basic principles which are involved during the phase transformation. So, as we know that there will be phase changes even in case of welding, where we call normally about fusion welding processes. So, there also there is a phenomena of phase change. So, you will have if you are trying to join two pieces. So, initially they are in solid state, solid phase. Then once you heat them, I mean a certain zone is heated, then that converts to liquid phase, and further as there is a change in temperature, drop in temperature after being exposed to surroundings, then there will be further transformation from liquid phase to solid phase. Now, we all know that this is all governed by certain principles. Why certain material is in solid state or in liquid state at any temperature, this is all governed by the free energy concepts, and how there will be phase transformation, what will be the mechanism of phase transformation, with what way the phase transforms. So, we will have certain discussions in this lecture about those points. So, coming to the introduction about that. So, as we know that the phases in the material that may undergo changes as a function of temperature or pressure. So, the change of that phase normally what the material is undergoing, that will be known as the phase transformation, and the control of a structure and hence the properties of material is often achieved by deliberately inducing or suppressing the phase transformation. So, as we know that when there will be liquid to solid suppose state transformation, now in that case we will have the light later on in this lecture that that often occurs by the process of nucleation and growth. So, and basically that's what we call it. So, the end result will be having certain structure, and at micro level that is known as microstructure. So, now this type of microstructure which is achieved, or the properties which are the result of the type of microstructure you get. So, that is basically achieved by deliberately inducing or suppressing the phase transformation. So, phase transformation, if you allow it to happen in normal manner, then the structure may be something, and then if you try to alter it, you alter the rate of phase transformation, speed of transformation, then the structure will be different and associated properties will be different. So, that is how. So, the time taken, that will be depending upon the nature and the mechanism by which a phase transformation is brought about. So, by what mechanism that phase transformation is brought about, and the free energy change during the transformation also determines its rate. So, basically we should know that the free energy change which occurs, that basically will be determining the rate of phase transformation. So, we might have the understanding about the free energies because at any temperature or so, at any material is in solid state or in liquid state. So, that basically is governed by the free energy value. So, if you talk about say free energy, so what we might have this idea that if you talk about liquid to solid transformation, liquid, if the liquid is converting to crystal phase, suppose beta crystal is being formed. So, we can see that if this is your free energy, and so this is G, and if you take this as temperature, So, any material if it is in any phase or state at any temperature, it is all governed by the phase free energy values. So, the free energy values go like this. This is your equilibrium temperature, or you can have so that is normally the melting temperature. Now, if you know that so this is after a melting temperature. So, this is basically the free energy for the liquid phase, and this is free energy for the solid phase. Suppose solid crystal B is beta. So, in that case your below the equilibrium temperature, you see that this line is for the free energy of the solid phase or beta. So, below the this equilibrium temperature, this free energy value of beta, that is solid form, is less. So, material exists in solid state, and once you increase the temperature after this equilibrium temperature or melting temperature, so in that case the liquid state or liquid phase has the higher lower free energy value. So, it comes into liquid states. That is how the material exists either in the form of liquid or solid phase, and we can say that whenever any transformation has to occur, so what is being said. So, if you go to our next slide. So, for a transformation of liquid phase to solid phase, at the equilibrium melting point the free energies are equal. So, that is what it is clear. We have seen that when the curves are meeting at the equilibrium temperature or the melting point temperature, at that point the free energy value of the liquid as well as the solid phase, they are equal, and there will be no transformation occurring, because the solid and liquid both are existing in equilibrium there. Now, if you take the temperature above the melting point, then what we have seen that there is liquid which has the lower free energy, and so the free energy change for the transformation is positive, certainly, because that change will be positive, and so there will be no transformation going on. Then if you take the if you take the temperature below the melting point, in that case the free energy change will be lower, because the liquid will have to come to solid value. So, if you take the free energy change value, so you know that in that case, so if you take this is your liquid value. So, if you have to change from liquid to solid, and if you take so that free energy change value will be positive. So, there will be no transformation after this temperature, while if you take the temperature below, since the free energy value of the solid phase is less than the liquid, so the free energy change value is negative. So, that is why once you have the temperature less than the melting temperature, then there will be transformation proceeding from liquid state to solid state, and that is the essential mechanism of having the phase at any temperature, in what phase the material will exist. So, now what we need to know that this mechanism by which this transformation has to occur. So, that is by the mechanism of nucleation and growth. So, when the magnitude of this free energy change is very small, the reaction proceeds very slowly. If you talk about the scale of transformation, time scale changes of the transformation. So, the magnitude of the free energy change, what we have seen, if this is very small, then reaction will proceed very slowly, and with a large supercooling below the equilibrium melting temperature, the magnitude of free energy change will be large. So, if you take the equilibrium melting temperature, and from there if you have the temperature quite less. So, if the degree of supercooling is more or undercooling is more, that is difference between that equilibrium melting temperature and the temperature which we are talking about, in that case you will have very fast transformation. So, and if it is very small, in that case the reaction will proceed very slowly. So, you will have many kind of if you talk about the qualitatively the transformation scales, in that case if it may take time from milliseconds to years, and that will be representing the also that what kind of transformation it is, whether it is very fast, whether it is fast, moderately fast, or whether it is slow or it is extremely slow. And depending upon that you will have also the concept of suppressibility of these transformations. So, when the transformation is extremely fast, it is occurring in the term of microseconds, it cannot be suppressed. So, it is insuppressible, whereas below that if it is very fast, if that takes time maybe from milliseconds to seconds, in that case it may be suppressed by very large cooling, and then it is suppressible in the normal case when you have slow transformations or you have fast transformation. That way it can be suppressed, and when it is extremely slow, then in that case the suppressibility is normally not possible. So, in that case basically transformation is virtually impossible, because the it is extremely slow in nature. So, you have many methods to go. You must have seen that in normal case you are cooling in the air, or you can go to cooling in the water. You go further to increase that by cooling in the oil or brine solution or so, and you have splat cooling, which is very extremely high cooling rate or so. Now, we will talk about so the next point which is important is that transformation is divided into two discrete phases, and these two discrete phases are that you have the formation of tiny stable particles, that is known as nuclei, and then further the growth of these particles, so that is known as growth. So, with that mechanism basically your transformation is basically complete. You have transformation is complete by the mechanism of nucleation and growth, and we will have certain understanding about the concept of nucleation and growth. So, as you know that if you have a liquid domain, if you have a domain filled with liquid, in that case you have everywhere you have liquid. Now, when the temperature will come down, in that case and it will come down below the equilibrium melting temperature, then there will be transformation started from liquid to solid phase. Now, as we know that when the solid crystal has to come out of the liquid phase, so that will be by the birth of a new phase. Now, any new phase, if it is created, it requires energy to be supplied. So, that energy it has to be supplied during the transformation. And if you talk about a very small tiny particle, in that case and if you assume the particle to be spherical, then the surface area by volume ratio, that becomes, if you take the spherical particle, so it will be 4 pi r square divided by basically 4 by 3 pi r cube. So, it will be coming as 3 by r. So, basically when you have very small r, so if r will be approaching towards 0, so this ratio SA by V is moving towards infinity, very large. So, initially it will be preventing the formation of new interface, so that is why but then as this R, if your at one point of time this R, if it is more, in that case this as the R goes on increasing, then this certainly it will try to stabilize, and that will lead to. So, I mean, as long it is not able to sustain, it is known as embryo, and then when it sustains, that is known as the nuclei. So, and then after that there will be further addition of atoms, and then it will be subsequent process of growth. So, that is way the way this nucleation and growth phenomena proceeds. So, if you talk about in normal case, if you say, if you are talking about the nucleation, so in nucleation also you have two types of nucleation. One is homogeneous nucleation and heterogeneous nucleation, and this is heterogeneous nucleation. So, the thing is that in the case of homogeneous nucleation, your probability of nucleation at all the sites inside the domain is identical, and in heterogeneous nucleation the probability of nucleation at preferred sites are more. So, at certain sites they are more. So, in normal case when you have a domain and you do not have any preferred nucleation sites, so that will be homogeneous nucleation. If you assume that to be homogeneous for a homogeneous nucleation case. So, if you take the delta F as the free energy change, so if delta F is the free energy change because of the formation of a new spherical particle. So, it will be 4 by 3 pi r cube, and this will be delta G plus 4 pi r square and gamma. So, basically one will be positive term, another will be negative term. So, that is your volume free energy, and we know that it has to be negative for the transformation to proceed. So, where this, so that is why you have r as the radius of particle, and you have delta G as the Gibbs free energy change per unit volume. And if you talk about the gamma, so it is surface energy per unit area. Of interface separating the parent and product phase. So, you know that this will be positive term, and this will be negative term, and you will have a free energy curve. And that curve basically what happens that initially when it is very small value of r, then this value will have very large value and positive value, and when as the r as the radius of that nuclei increases, in that case you will have so ultimately as the r increases, this term starts dominating, and then your resultant delta F curve will go on decreasing. So, you will have a point at which after which it starts decreasing, and that is the point from where the transformation is supposed to start. Now, so for getting that point, so what happens that if you talk about the free energy, those values. So, if you take this as the positive and this as the negative values. So, what happens initially when you are for a small, very small value, this is going towards very high infinity, but then once you and if you take this value, normally it goes like this. So, this will be 4 by 3 pi r cube delta g plus 4 pi r square gamma for this side. Now, this is the point from where it starts going on decreasing. So, for getting this point, what we do is d by dr of delta f, we are doing it, equating it to 0 for getting this value of r. So, this is r basically and this is delta f. So, if you do that, we get basically so for that we are calling it as r star, and this will be minus 2 gamma by delta g. So, so this is known as the critical radius in this case and of the nuclei, and for this the delta f star also its critical value. If you put these values into this expression, so it will be 16 by 3 pi gamma cube by delta g square. So, this is what the value you are getting for the delta f star values. Now, you can have another also expressions for these delta f star or for the transformation also. Now, if the radius, so this will be your critical radius and that will be known as RC star. Now, if the radius of the particle is below this line, towards the left, in that case it is known as embryo, and if it is after that, it is said to be nucleated. So, then that is basically the nuclei. There are another also expressions for liquid to suppose the beta transformation. So, if you talk about for liquid to beta transformation, so you have another simplified relationship that holds good is delta G equal to delta H into Tm minus T upon Tm. So, basically it will be delta H into delta T upon Tm. So, basically delta H is that it is enthalpy change, or we also know it as heat of reaction per unit volume of the product, heat of reaction. So, that is per unit volume of the product, and it is independent of temperature, and Tm is the equilibrium melting point, and at Tm basically this delta G, certainly if you talk about at Tm, so it will be delta T is 0, so delta G becomes 0. Now, if you use this formula, so you get the expression for delta F star, that will be 16 by 3 pi gamma cube and Tm square upon delta H square and delta T square. So, this is another expression for which by which you can get the value of delta F star, that is your this barrier and that will basically be affecting your nucleation process. Now, further, so that will be just this gives you the concept of delta F star. Now, the thing is that when you have the number of critical sized particles, that basically can be estimated using the Max Boltzmann statistics. So, that statistics concept is used, and from that Max Boltzmann statistics, if you try to find the the number of these particles, so if you have to estimate number of critical sized particles. So, for that the Max Boltzmann statistics is used So, what will be the number of critical size particles in the parent phase? So, if Nt is the total number of particles per unit volume, of parent phase, in that case if you have to find the number of critical sized particles. So, number of critical sized particles, that if you denote by n star, so it will be denoted by Nt, and this will be exponential of minus delta F star divided by RT. So, this will be the value of the number of critical size particles, and the process of nucleation is that is that step of process when this critical size particle becomes supercritical. So, that will be by jumping off one of the atom from the parent phase to the product phase. So, that basically will make it supercritical. You have a critical size particle, and then you have adjoining atoms on that interface, and from that parent phase or the liquid phase, one of the atom will jump into that critical size particle, and that will make it supercritical, and then it is said to be nucleated. So, if suppose in that case, if suppose this is your product phase and this is your parent phase. So, if this is your product phase and this is your parent phase where you have atoms, and this atom has to jump from there to make it super critical. So, if suppose you have S star atoms which are which are facing that interface, and if one of these S star atoms is basically jumping into the product phase, then it is said to be nucleated, and for that again you are using again this statistical concept, and the frequency with which any one of these S star atom that will be crossing that interface. So, this nu dash, so if you take nu dash as the frequency with which any one of S star atoms are the number of atoms which are basically facing this interface or in that parent phase towards the product phase. So, if they are the atoms can cross the interface and join the product phase. So, if that is your nu star, so this nu star also will be taken as S star into nu and exponential of minus delta HD upon RT. So, nu is the lattice vibration frequency. So, nu is lattice vibration frequency, and S star is the number of atoms which are basically across the interface which are touching on that surface, and delta HD is the enthalpy of activation. So, delta HD will be enthalpy of activation for diffusion across the interface. So, if you look at this nu prime value, now that will be S star nu exponential minus delta SD by RT. Now, the thing is that if you talk about the rate of nucleation, so the rate of nucleation of the new phase particle, so if you talk about it, it will be so that will be dN by dt, and this we also call it as the I, and it is nothing but the product of the number of critical size particles. So, it will be a number of critical size particles and multiplied by the frequency with which they try to become supercritical. supercritical. So, we have got the expression for that, and it will be n star and nu prime. So, it will be nt s star nu exponential minus of delta f star plus hd and divided by RT. So, that basically is talking about the expression for the rate of nucleation, and what we see that in this basically this pre-exponential term value, it's coming in the range of 10 raised to the power 42 meter raised to the power minus 3 per second, and then depending upon these values your nucleation rate will be defined. So, basically if you talk about the conditions, like if you are talking about the equilibrium melting temperature, in that case at that point you will have this value as so depending upon that this delta f star or hd. So, depending upon these values at different temperatures. So, what is seen that when you are at a temperature near the equilibrium temperature, at that point also if you see the rate of nucleation, this rate of nucleation is basically 0, and if you go to the absolute 0 value here, in that case also it will be this value will come out to be 0. So, what is seen is that if it is temperature and if it is 0 Kelvin and if it is your equilibrium temperature, then what is seen is that your nucleation will proceed from here, and then after certain time basically when this RT term starts dominating, in that case then it starts decreasing further. So, and then it will come to 0 at the 0 term. So, this is how the rate of nucleation will be curve will be shown. Similar will be the curve for the growth, and for growth basically it will be similar, but it starts this becomes predominant when you have the temperature in the upper zone. So, your growth also has a similar curve, but it will be more when it is near to the equilibrium temperature, and depending upon these two you will have the transformation curve. So, so you will have the transformation curve dx by dt which will be in between the two. So, this is the concept of transformation in between in the case of the materials. Now, so this was the concept of transformation in the case of homogeneous nucleation. When we talk about the heterogeneous nucleation, now heterogeneous nucleation at preferred places you will have the chances of nucleation will be more, and that is basically governed based on the the particle which is nucleated and the interface which is created. So, taking upon the surface tension forces also into account and other factors. So, summation of forces if you read them from some standard books. So, the thing is that the energy which you have to supply for creating the surface in the case of homogeneous nucleation, that basically is less in the case of heterogeneous nucleation, because here you have certain surfaces present. Now, that may be in the form of inclusions, or that may be the wall of the container, which is basically the sand, basically sand molding material. You have inclusions. So, so basically in that case that becomes your source, and from there the nucleation is basically assisted. So, the delta F star value which you are getting in the case of homogeneous nucleation, in the case of heterogeneous nucleation it may be so maximum it will be the same as homogeneous nucleation for certain cases. However, depending upon the characteristics of the product particle and the interface or so, you will have the delta F star requirement will be lesser, and that will be basically giving the ease in nucleation, and that is why that is the concept of heterogeneous nucleation. So, so we will be, whenever we will be talking about the transformation of the from one phase to other. All these things must be in our mind, so that we can correlate that what might have happened. This is from the liquid to solid state. Similar thing happened in the case of solid to solid state transformation. Now, in those cases you have other strain energy factor is coming into picture. So, basically there also you will have nucleation, and you may have nucleation at certain points. Many a times what we see that you have certain preferred places where the nucleation starts, and that will be at those higher energy places, like you have grain boundaries or the dislocation sites or so. So that will, so basically depending upon that free energy values concept, and also other whatever we have understood, we must have the clarity of these concepts in mind, so that it will assist us in the understanding of other metallurgical processes or the welding processes in a better manner. Thank you very much.